So, thank you very much, Daniel. Thank you for everyone for coming along today. The Abraham-Minkowski controversy. So, this isn't actually my main topic of research. I'll say that it's something that one of my graduate students. It was a problem I wanted to learn about, and I put one of my graduate students onto it. And he is here. Where is Nick? Oh, there he is. And Daniel was the external examiner on this and on Nick's PhD, and thought, oh, that would make a nice colloquium topic. So here we are today. All right. So this is Abraham, and this is Minkowski, or probably I should pronounce it Minkowski. That's not the controversy, by the way, as to which one is which, but sometimes I have to think. This is, as Daniel said, a 100-year-old or so controversy, and I will explain that, and most of the colloquium will be on that. But towards the end, if I don't run out of time, I want to describe some of our own work with Nick that we've done on this, which is trying to use quantum, bring in some quantum aspects to the story, because it's basically classical physics as it's in its original formulation. Okay. And I should say that the first place I heard about it and learned about it was in this very room, just like you guys, which was back when I did a year's postdoc with Alan Griffin, and along came Peter Maloney and Paul Lett to give a joint colloquium on how does the photon get its momentum. Except, as I remember, Peter missed his plane or something like he missed the first. So I can't remember if one supported Abraham and the other Minkowski, and so we got a very biased point of view. But I remember they didn't both make it on for the first event. But then, okay, and actually you can find their talk on the web if you look. All right, so here's Nick. After he finished his PhD, this is the first time I've seen him. I think this is him in a nightclub in Cuba shortly after his Viva. Anyway, so that's the main acknowledgement to Nick here. Okay, so I'm going to introduce the Abraham and Minkowski ideas, and I'm going to talk specifically then on two experiments. So this is generally a complex subject, and the reason it's complex is it deals with light in media. And media are complicated things, and actually far too complicated for me. So after really introducing it, I'm going to specialize into a very much simpler system, which are ones I understand better, which is ultracold atoms, where this Abraham-Minkowski controversy, I think, takes a particular simple form. Hopefully not too simple, but it's simple. And in particular, yeah, so after we've done, so I'm going to try and convince the experimentalists in the room that this is an experiment that's absolutely waiting to be done. Looking at a couple of them over there. and then we're going to talk about then some more quantum experiments that might see some new stuff. Okay, and including a proposal at the end of an experiment. I'm not going to get down on my knee or anything. All right, so what this is really about is optical forces on matter. And this is a big field, but you may not know. So these optical forces tend to be very important on small scales or very large scales. So it was Kepler back in apparently 1619 who postulated that the reason that comet tails always point away from the sun was due to radiation pressure. And that turns out to be partly true. In fact, there's also the solar wind and so on, but radiation pressure is part of it. NASA is planning to put up satellites and spaceships that will travel through the solar system using solar sails. And I guess in more recent times, well, this is recent, but in more recent times, these optical forces are quite generally known in science through something called optical tweezers, which is where you have a laser beam and you focus it down, and what you find is that particles, not atoms now, but generally, I mean, atoms is one example, but particles that are polarizable tend to get pulled into the most intense region. They like to be in the focus of this beam, and so people, for instance, they stick dielectric spheres on the end of strands of DNA, and you can use this to pull apart DNA and do some very nice experiments. So it's used in biophysics, for one example. You can also rotate up molecules by using light with rotational properties, with angular momentum. And then really in cold atoms is where optical forces are really, the whole field relies on it, basically. So laser cooling, you first have to cool your atoms right down to the order of microkelvin. So counterintuitively, you can cool atoms down by shining lasers at them, but you do it in the right way, and you cool them, use the momentum of the photon to cool down the atoms. And then after you've done that, you can then trap the atoms. So Joseph and Ephraim have this next thing in their labs. They use optical lattices to trap their atoms. Another example of optical forces is in optomechanics. And this is where, for instance, you might have a cavity made of two mirrors, and you shine a laser in from outside, but one of the mirrors is on a spring. And so you can have lots of nice systems like that where you, but in particular, one important example of this that came up this week, is LIGO. So it turns out that the LIGO is, as you know, an incredibly sensitive instrument for detecting these gravitational waves, but a very significant source of error in that is the radiation pressure on the mirrors. And people have to worry about that. And for the next generations, that will be, as they get more and more sensitive, that will be an even bigger problem. Okay, so let's start kind of from the beginning. And I'm going to swap sides to over here. So I can see the clock. Okay, so momentum of light. So where I'm going to start from, and where I hope you may have heard, is the Poynting vector. Okay, so this is the energy flux in an electromagnetic field. So the amount of energy crossing unit area per unit time. And in vacuum, this is E cross H. And so if we want to ask what is the amount of energy, for instance, if we want to go from there to a momentum density, and this is the controversial part that is the momentum density. So what we might do is we say, okay, we have the amount, we imagine the amount of light crossing something with unit area, and it's going to in 1 second it's going to trace out this volume, this cylinder of length c. Okay, so the amount of energy then in this cylinder is going to be S, and the energy density is the amount of energy divided by the volume. Because we've got unit area, we just need to divide by c, and then to go from an energy density to momentum density, we need to divide by c, so we get S over c squared. And so then we get this expression for the momentum density in vacuum is E cross H over c squared, and that's not controversial. And then we go to a medium. And in a medium, you may have heard, you may remember from your undergraduate lectures that, okay, we have these extra fields. We have this displacement field, D, we have the flux density B. So which combinations of these things do we choose? Is it still E cross H over c squared, or do we use some new combinations? And so this is the controversy then. So Abraham said, okay, it's basically the same form as in vacuum, except, of course, E and H may change inside the medium, but it has the same, you write it in the same way. Whereas Minkowski said, no, it's D cross B. Okay? And so this is the source of the controversy. And why is this, 100 years on, why is this a controversy? And the basic reason is media are very complicated, optical media, dielectric media, and we really don't know, once light or electromagnetic wave in general enters a medium, how the energy and how the momentum, some of it goes into exciting the atoms, and you get some polarization. So some of the momentum goes into the material, really somehow into internal motion, into internal excitations and so on, and the whole material moves. Some of it is still in the light field, and it's splitting those two up, which is complicated. And I should say there's other forms too, so Einstein and Lieb had their version of it. Okay, and so what physically, so personally, so the way Minkowski and Abraham worked, they worked with looking at symmetries of stress energy tensors and so on. It's quite complicated, and personally, I don't get a lot out of that way of viewing things, but I do get a lot more out of this way of viewing it. So it turns out that, I'll sort of justify it in a hand-waving way, that the Abraham version of the momentum density, you can think of it, it's not a quantum property, but it's often useful to think about photons. So if you have a photon, which in free space would have momentum h bar k0 out in vacuum, then Abraham says, well, once the photon enters the medium, its momentum gets reduced by the refractive index, n. Meanwhile, Minkowski says, no, it actually gets increased by the refractive index, n. So these two look, who knows what that means, but this, I think, is quite clear that it's somewhat different. Okay, so here's a hand-wavy way of justifying this. So imagine what isn't controversial is the energy. Okay, so the energy inside a medium can be written in this way. And if we just for a second think that this is, we've quantized the field, why not? Then we can think of a single photon in our volume. Now, the energy on average is shared equally between the electric and magnetic parts. Okay? And so, so we can say that then the magnetic part is equal to the sort of electric part, and they're equal to h bar omega. Okay. So now let's think what happens in a medium. If we have an electromagnetic wave, what happens is the wave number k goes to n times k. Okay, so in other words, the wavelength gets shorter. That again is not controversial. So that's for both the E and B fields. This will happen. And so when we substitute this form of a wave into the Faraday law, then sort of very schematically, what you have then when we take these derivatives, you have this form for the relationship between E and B. And then we can divide through. If we divide through by k, then omega upon k is c. Let me just write that up. It's an important one. Okay. All right. Omega upon k is c, but then we also divide through by n, and c upon n is c prime. It's the speed of light inside the medium. Okay, so now we go to the sort of left-hand side here. We have bh is equal to h bar omega. And let's divide both sides of this little equation by nc. Okay, divide through by nc. And then we say, okay, in fact, n is c over c prime, so we can rewrite it this way. So we change this n into c upon c prime. So we get divide by c squared and multiply by c prime. And then c prime times b, well, that's e. So we replace the b times c prime by e. We get eh upon c squared, and that is equal, because what we did on the right-hand side, again, omega upon c is k. We get h bar k upon n. Okay, so that is a sort of hand-wavy justification for the Abraham result. Okay, although it's not the cross product in here, it's got the right scaling, basically. E and h over c squared is integral of that over the volume is h bar k upon n. Meanwhile, you do the same thing. If you do the same thing with Minkowski, what you get through to is that this integral of d times b is n times h bar k, which is what is claimed here. So that's a kind of hand-wavy way, but, what intuition does that give us? Not too much, in fact. So let's go a little bit further. And what one finds is that the Abraham can be associated with a particle picture. The Abraham view is associated with a particle picture, and the Minkowski is with a wave picture. So what do I mean by that? So let's imagine that our light can somehow be described in terms of particles with a momentum. They're traveling at speed in a medium c prime, and let's say they have some mass. Okay? Hold your disbelief for a second. Let's say it has some mass. C upon n is c prime. Well, we know how to relate energy and mass. That's what Einstein taught us. And so let's just substitute that in. Okay, so then we replace the m by e of c squared. The c squared, part of the c squared is going to cancel. We have e upon nc. And then finally, we've used some canons here, right? We've used Einstein. Let's just go the whole way. Let's use Planck. So we use Planck. E is h bar ck. Stick that in. And we get exactly this result. So that really, what this leaves us with is a sense that Abraham is somehow associated with particles, and indeed that's the way things seem to be in experiments, that it's associated with center of mass motion of light. I'll hope to clarify that notion a little further soon. Meanwhile, Minkowski, well, that's direct. To get this, you just, it's what you may have already believed before you came in here. Well, lambda inside a medium, the wavelength just gets shortened. So in other words, k goes to nk, stick it in. And notice that this is all waviness. This is a wavy kind of idea, okay? Okay, so there's been a very large literature over the years on this, and these are just, so it goes way back to 1908 or so. But these are some of the recent papers that have come out, and it's still going. In fact, there was an experiment, the most recent experiment was done, it's coming up in, I think, 2014 or so. And actually, this review here has a reference to the Maloney-Lett colloquium here. It has a citation to that. So there you go. Okay, so here I'm not actually, these are the very complicated experiments that I'm not going to go through in detail because I'm going to go through some much simpler ones. But the sort of modern era, I think, began in 1954 with the famous experiment by Jones and Richards. Here they were looking at the recoil of mirrors inside fluids and seeing if they had a sort of mirror on each side of a spindle, and one side of the mirror was in the fluid and the other one not. And they looked at they had this on a torsion. They looked at the imbalance of the forces on this mirror in the fluid, and they found that it depends on the refractive index of the fluid, so that one sort of agreed with Minkowski. Another set of experiments, you shine light onto the surface of a liquid, and you look at whether the liquid bulges outwards or inwards. If it bulges out, that's a sign of Minkowski. If it bulges in, it's Abraham, and they came out favoring Minkowski. And then there was a Canadian experiment in 1975. Of course, to this stage, everyone else had favored Minkowski, and having now lived in Canada for 11 years or so, of course the Canadians supported the underdog. You know, they wanted to balance everything to be fair, and so they came out with Abraham. So this one was you have a time-varying, so you have a constant axial B field and a time-varying radial E field, and you're looking at torsion on some disk, and how the torsion, again, measuring forces on this disk due to these fields. And they came out with Abraham. And much more recently, in 2015, there was an experiment where they, again, were doing lasers shining off surfaces of liquids, and they came out with Abraham. Okay, but I'm going to go for two much simpler experiments that hopefully we can understand right here and now. And so one of these, again, one is going to support Minkowski, and one is going to support Abraham, but I'm going to reconcile them. I'm going to explain why they sort of give why it's not as mysterious as it looks. And one is going to be based on diffraction, and as I said, diffraction and waviness, wave behavior seems to favor Minkowski, and whereas center of mass motion, in this sense we mean a light pulse, center of mass of a light pulse is going to favor Abraham. Okay, so the diffraction case first. So here we have a setup where we have a beam of atoms, and it's being diffracted off a standing wave of light. So this is the reverse of the normal situation. You might think of light diffracting off a material grating. Here we have matter waves diffracting off a grating of light. And this grating of light is made of two counterpropagating lasers, both with wave number k. Okay? And now, okay, so what happens, you can think of, the original idea for this, it's called Kapitza Dirac scattering, because the original idea was proposed for electrons by two very famous people in the 30s, but it was then finally done with atoms in the mid-1980s. And so the idea is that an atom can absorb a photon from one wave, so it gets a plus k kick, let's say, and then it gives that photon up to the counterpropagating wave. It's stimulated. It's a stimulated process. So then because it's taking from one wave and giving to the other, it gets a 2 h bar k momentum kick. But now imagine increasing the density of these atoms until they sort of form a medium for the light. And so then we ask, well, is this momentum recoil do we multiply by the refractive index n or divide by it? So that was the question. So this challenge was taken up by some very eminent people. So David Pritchard at MIT and his former graduate student Wolfgang Ketterle, who is a Nobel Prize winner for basically making Bose-Einstein condensates. And Gretchen Campbell, she's also a professor now in Maryland, and so lots of famous people on this paper. And so they did basically that. There are a few more bells and whistles, but this was the idea. They had a Bose condensate, so you have a dense as gas of cold atoms as you can kind of have. And they found that they caused the condensate to diffract when they shone on these counterpropagating lasers, and they got unequivocally 2n h bar k. So this n is the refractive index again. So they seem to favor Minkowski, but we will revisit this experiment shortly. Okay, so that's one for, I should write one under Minkowski. Okay, but then comes along this experiment. Now this is the one that is, okay, it's a thought experiment so far, but it really should be done by somebody. And so this is considering now a single atom. So if we want to understand a medium, what's the simplest medium you can have? Well, a single atom. That's a simple medium. And you imagine now a pulse of light coming along, hits this atom. Okay, so this atom is dielectric medium. We can describe it, the polarization term is just this, the dipole of the atom, and it's located really at the atom. And we say that the atom's not magnetic. So which way does the atom recoil? So imagine that this light is red detuned from resonance. Let's take a poll. What do people think? What do the experts think? Which way do you think it should go? So remember what I said about optical tweezers, if you remember that, with particles, polarizable particles being attracted into the most intense regions of the field. So let's have a show of hands. Who would guess that the atom's going to recoil to the right? Anyone? 1, 2, 3, 4. Okay, and to the left? Okay, so I must say, when I first saw this, I also thought to the left, because there's the force on the, as I said, the atom would like to get pulled into the most intense part of the field. So you might think, okay, the atom's sitting there, along comes this wave, it feels this gradient which pulls it in. Once it's completely enveloped in the wave, nothing happens, but it's already got this momentum kick, so it's traveling along, and then it'll give up its momentum when the wave has passed. But in fact, that's not what happens. It gets kicked to the right, according to this thought experiment, and that's why it should be done in the lab. And so let me explain why I think that's true. Okay, this is a little bit of a busy slide, but I'm going to skip a few steps. So these systems are simple enough that you can really think about the Lorentz Force. Okay? And the simplest model of an atom is as a dipole, and you can think of the total Lorentz Force. Okay, there's a contribution to the electric field and V cross B here. So it acts, it's acting both on the positive charge and on the negative charge. So the total force is going to be the sum of the two, okay? And, but because this dipole is very close together, we can basically Taylor expand our field, and in this way, we get down to this expression, and then I'm going to assume linear response here, so I'm going to assume the dipole is proportional to the electric field with the polarizability in there, and then we reduce the form of our Lorentz force to this equation here. And this is still not in a form that most cold atom people might be used to, and people that work in these optical forces. So you can do another little transformation with some vector identity, and again with Faraday, and you get down to this form. And almost all people, at least in my field, they don't think about this term at all. They just think about this term. So this is the gradient force, this one here, and it depends on the gradient of the intensity. And this is the thing that you think would pull the atom to the left. Okay, it will pull the atom into the intense region. But there is this second term here, and it depends. So E cross B, well, that's nothing. That's directly proportional to the pointing vector. And so this term is proportional to the time derivative of the pointing vector. And where does this come from? This comes from the fact that if you have an atom which is being driven by some external field, you get an internal current inside the atom, this oscillating dipole. And then the effect of the magnetic field on that current gives this extra term. That's one way to understand it. Okay, so then we have these two terms. All right, so this one gives the gradient force. So going back to writing it the same thing, but in this way, so the force in a particular component, so we get the gradient term. But then this other term, what you find, and I'm not going to go through the details, but it's a relatively simple calculation that I don't think is in any way controversial, but it's in this paper by Barnett and Hines. You find that this contribution for this particular setup is twice the magnitude of the gradient force, but in the opposite direction. And so it pushes the atom away. And so, for instance, if we look at what is the impulse, so that's momentum transferred, that's the integral of the force times the time, well, this is just proportional to the time that the gradient force acts. Whereas this one is proportional to the total change in the field strength. When you integrate this over time, this time derivative goes. And so we're used to, if you have some static configuration of fields, you're used to this one just slowly builds up over time, and just as long as you have the system on, this one's going to build up. Whereas this one just, if you have a static configuration, isn't going to change. You're not going to see that this one's going to be 0. And even if it changes, well, it's limited by the total change. So you do not see this term appearing in the Bible of sort of atomic, one of them of atomic physics, this book here. They do not discuss it at all, because normally it's not relevant for typical cold atom experiments where the gradient, where you have static field configurations and so on. But this is an example where you do have to keep this extra term. Okay, so what does this, if I say it gets kicked out of, away from the wave, what does this correspond to Minkowski or Abraham? And the answer is it actually corresponds to Abraham. And you can sort of see that, well, firstly, Abraham, remember, you reduce the momentum, so you divide it by the refractive index. And so if the atom is getting a kick this way, because what is not in doubt is that the total momentum must be conserved, right? So if the atom is getting a kick this way, it must mean that the momentum of the photons is being reduced. And so that immediately tells you, without going through the details of the calculation, which I'm not going to, it tells you that it must be, well, it could be something else, but it turns out to come out exactly to the Abraham version. Whereas if the atom was getting pulled this way, then the photons would get an extra momentum, and that would be Minkowski. And so, for instance, if we compare now with our Minkowski expression, remember it was D cross B, right? So we substitute in D and B in there, and we find that we reproduce then the E cross H over C squared. When you remember that mu times E naught is 1 upon C squared, we get the Abraham momentum density. But then we get this extra term, this D cross B. So with this very simple medium, writing it like this way, the difference between the Minkowski and the Abraham is exactly this D cross B term. And when we do the integral, this is the momentum density. When we do the integral over a volume to get the momentum, we get then literally the difference between the two is D cross B. So the D cross B term is completely responsible for the difference between Abraham and Minkowski. Okay, and the Lorentz force, which is sort of a microscopic picture, predicts Abraham here. Okay, and as I said, the check is for the reason I said that if you were to drop this D cross B term here, drop it out of the problem, then the atom doesn't get so much doesn't get so much of a kick to the right, and you must have. So if you didn't have that term, you would get, in fact, Minkowski, because that you would no longer be taking so much momentum away from the light. Okay, so so I say this is Abraham, but didn't that Nobel Prize winner, Mr. Ketley, tell us that he got Minkowski out? How do I reconcile that with what happened? Well, the answer is that, remember this D cross B, in linear response theory, D is proportional to the electric field. Okay, so D cross B is this guy, which is proportional to the pointing vector. And that is the difference between Minkowski and Abraham. And the thing is, in this experiment, there is no pointing vector, because you have no net pointing vector. You have two counter-propagating waves, and you have a standing wave. So there's no net pointing vector. So in this particular experiment, it's not a way to tell between Minkowski and Abraham, because this term is 0, and you get the same answer for the two. Okay. So let's keep trying to understand how this might come about. And so there was this paper in 2010 by Stephen Barnett where he announced, Abraham-Minkowski has been resolved. Now, I think I would agree with him that it has been resolved. So what isn't in doubt is that the total momentum is conserved. Okay, so if you ascribe Minkowski to the light, then you must have a particular momentum for the atom, such that if you were to subscribe to Abraham for the light, you would have a different momentum for the atom. But the total in both cases must be equal. Total momentum must be conserved, whichever you choose. But what he says in his abstract here is that Abraham is associated with the kinetic momentum of light, whereas Minkowski is the canonical momentum. So in fact, in this, we replace this by the canonical momentum and the kinetic momentum. And in fact, this idea has been around for a long time. It probably goes back to unpublished work from 1971, but it's also explicitly discussed in many other papers. So I don't think he's claiming that he has resolved it, but he wanted to make clear that to everyone that it is resolved. And so the resolution essentially is whether you're measuring the canonical or the kinetic momenta. So how does this come about? How can we understand this? So I'm going to revert now to a Lagrangian. So this is the Lagrangian for a charged particle. So not an atom now, but just a charged particle. You have a kinetic term, but when you put it in an electromagnetic field, it couples in minimal coupling via velocity to the vector potential, and then you have your scalar field. So the canonical momentum is defined as the derivative of the Lagrangian with respect to the velocity. And you see, if you do this, you get something, if it wasn't for the electromagnetic field, if there was no electromagnetic field, this term would be 0, and you would just have the canonical momentum was equal to the kinetic momentum. But in the presence of electromagnetic field, that's no longer true. The canonical and the kinetic differ by this term here. So this is sort of the context in which people are most used to seeing the difference between a canonical and a kinetic momentum. How about for a dipole? Well, I'm going to switch. So I'm going to write down now the Lagrangian for a dipole, not in minimal coupling, but in the dipole formulation. And here, the energy of a dipole in a field is minus d dot E. So I still have the kinetic energy term. The Lagrangian is T minus V, so we get plus d dot E. But we've got to be a little bit careful, and we've got to ask what really is the field that the atom sees, or this dipole sees. And it's, in fact, not the lab frame, but the field it sees in its own frame. And that is shifted by a Lorentz shift, so that the actual motional field picks up this extra bit proportional to the velocity and the magnetic field. Okay, so then when we perform the same derivative and we ask what is the canonical momentum for this dipole, so we take the derivative now of this guy with respect to the velocity, we get the canonical momentum, and again, so it's equal to now the kinetic part, but now what's playing the role of the vector potential here is exactly this d cross b term that kept cropping up. Okay, so this mysterious d cross b, in fact, it's called the Röntgen current. Historically, d cross b, to give it a name. And that's basically the idea. And so we can build up this map between, we can pretend, in other words, that a dipole is behaving a bit like a charged particle. Okay, but we have to associate, we say that what in reality is b cross d, well, we can pretend, in this pretend picture, what is playing, we can associate that with a sort of fake vector field, QA, and then D dot E is we can describe this via a fake scalar potential. And then we can define effective field. So this is the normal relationship between the electric field and the scalar field and the vector potential. We just apply this in this scenario, and we get back exactly this term, which was the force we got in the Lorentz picture in some of the earlier slides. And meanwhile, the effective magnetic field is the curl of this vector potential. And we get then the curl of this Röntgen interaction, this D cross B, or written the other way around here, B cross D. So, for instance, does this work? Let's look at the force on an atom in a plane wave. So, if we have a plane wave, remember this B cross D. If we replace D by alpha, by the polarization times the electric field, this is just the pointing vector. And so, in a plane wave laser, the curl of the pointing vector is going to be 0. The pointing vector is just a vector that's going along with the wave. It has no curl. So then our effective magnetic field is 0. How about our effective electric field, where we follow the prescription that we saw on the last slide? And this is nothing other than this, so that the force on the atom then, what's left of the Lorentz force, because the magnetic force is 0, is just Q times this electric field. And that's exactly this term we got previously when we worked out when we looked at this dipole interacting with an electromagnetic field. So notice that that's for a plane wave, but we can get much more interesting situations. So say our pointing vector wasn't just pointing in one direction, but also had a component rotating around in the plane. And that's what you get, for instance, with a vortex beam of light, a Laguerre-Gauss beam that people can make. You put your light beam through a phase plate, you can get this vortex beam. Then you have some component, then you get some curl in your pointing vector, and you can get much more interesting stuff that I won't go into. Okay, so this is all classical stuff, and now I want to go to quantum matter. And what I'm going to claim is that there's a deep connection between this Abraham-Minkowski problem and basically a version of the Aronoff-Bohm problem. A version of it called the Hay-Mikela-Wilkins phase, in fact. So I'll just remind you, the Aronoff-Bohm problem is where you send electrons around a solenoid. You send them two sides around a solenoid. And with a solenoid, you should know that there's a magnetic field inside the solenoid, but there's none outside it. And so there should be no forces on this, no forces on these electrons, because there's no B field out there. And you assume there's no charges, there's no electric field either. And yet, mysteriously, when you do this experiment and you change the magnetic field in there, you find that the interference pattern here gets shifted. And so it somehow knows about the magnetic field in here, even though it's always in regions where the magnetic field is 0. And this is put down to the non-locality of quantum mechanics is one explanation of this. But if the way to calculate it is to say, okay, the B field may be 0, but my vector potential is not. And so this also is a way of justifying that potentials have a meaning in quantum mechanics that they don't have in classical mechanics. And you can exactly calculate what this phase shift is by the integral of this vector potential around this circuit. So this is the Aronoff-Bohm effect. Well, Aronoff was just warming up with that, because about 20 years later or so, he came up with the Aronoff-Kasher phase. So this is the Aronoff-Bohm, this is Aronoff-Kasher. Aronoff-Bohm, you can imagine a bunch of magnetic dipoles. Here they are lined up to make a solenoid. And you put an electron around that, so you have a charge. What happens if you reverse the roles of the charge and the electric bits and the magnetic bits? So now you have a bunch of dipoles, neutral now, so the dipole, neutral magnetic dipole, going in two paths around now a charged line, a charged cylinder. And you find that you again get, providing you confine yourself perfectly into 2 dimensions, you get a topological phase, which is called the Aronoff-Kasher phase. So this is a neutral magnetic dipole moving in a purely radial electric field, because the symmetry of this is such that the electric field is propagating radially outwards from this cylinder. So now there's yet another phase now, and by doing a duality where we now swap the roles of, we now consider an electric dipole moving around a cylinder of magnetic charge, so that the magnetic field is purely radial. And this thing was proposed in about 1993, 1994, Hay and McKellar and Wilkins. And so again, this is a sort of example of a topological phase in quantum mechanics. So if you arrange things perfectly in 2 dimensions, you can have a situation where there's no forces on this neutral electric dipole, right? It's an electric dipole. It shouldn't see this magnetic field, should it? You know, that's what you think. It shouldn't see this magnetic field, and yet you find that you get a phase shift like this. And of course, what's going on? Well, you know, in its own frame, it's seeing a transformation of these fields. In fact, going back to the Aronoff Kasher, this is nothing other than spin-orbit coupling, what is better known as spin-orbit coupling. That in this magnetic particle's own rest frame, it sees part of the electric field converted, part of the electric field converted into a magnetic field. So this is playing the role a bit like a bee, and then it's interacting with the magnetic moment. And so it goes here. But look, what is this object? B cross D. Did that come up in the last slides? It's exactly this Röntgen interaction. Now, the only problem with this, I said magnetic charge, and no one stopped me. And that's true. So with the original proposals, they were problematic because you needed a line of magnetic monopoles to get a purely radial magnetic field. And that's a problem. But it turns out some very clever people have figured out ways to get around that. In particular, as an experiment, so these guys, Jacques Viguet's group in Toulouse in France, figured out a way to get around it. And so what their system was the following. So they had an atom interferometer. So they have these atoms coming in. They have this standing wave of light. And here the standing wave of light is playing the role of a beam splitter. So it splits your atom beam into these 2 arms. And then it acts as mirrors here, and so they get reflected here. And then you get an interference region here. And you can measure if there's a relative phase shift between these 2 arms, then you can measure a phase shift down here. So they did this with lithium atoms. And the particular way they did it was so that they had the atoms pass through, in this region here is in fact a double capacitor, where you have a common plate in the middle, which is held at, say, 0 volts. And then the 2 plates either side are held at plus or minus that charge. And so this polarizes quite strongly. You have, well, I mean, lithium is not that polarizable. You have to put on 800 volts, and so that they polarize the atoms. So one arm gets polarized in one direction, and the other arm gets polarized in the opposite direction. And then they have a magnetic field which is coming out of the board. You don't see it in this picture, but it's coming out of the board. So they have this B cross D configuration where B and D are non-zero, and then and the point is that when you get this loop around, the 2 arms don't cancel each other out. You think, oh, don't you get the same phase of the 2? No, because they're oppositely polarized in the 2 sides. So you get a net. When you do your line integral, like in the Aronoff-Bohm around the whole circuit, you get this net contribution. This object here is not 0 as you go around. And it doesn't depend in any way on the velocity. Velocity doesn't appear in this, so it's a topological object. And so because it doesn't depend on the velocity, it really just depends on the path. That's a signature you can check that this phase is a property purely of the path you take, and that's something you can check in the experiments. And they were able to measure this effect, and what they were it's weak though, and what they had to do to measure it in these, just to show you how sensitive these atom interferometers are, they're basically measuring at the milliradian phase shift down here, and that's equivalent to measuring a shift in the wavelength of a part in 10 to the 4, which is about between 1 and 10 femtometers. So these are incredibly sensitive devices. But the point was that although this looks like the Abraham-Minkowski these were all static fields in this setup. Okay, so B and D are static. And so if we want to get a true sort of quantum version of the Abraham-Minkowski, if you like, we should do this with optical fields, because Abraham-Minkowski was, well, the full glory of it is in optical fields. And so this is where Nick's work comes in. So here we thought of a situation where now so remember the key thing, this D cross B for optical fields is this pointing vector. So the configuration we imagine now is you have an atom interferometer where you have an atom. Again, it's split into two paths by this standing wave of light. And one path is illuminated by a traveling wave of light, which has a net S, a net pointing vector. And the other path has a net pointing vector in the opposite direction. Okay, now, if they were going in the same direction, the effects would be the same in both arms, and they would cancel out. But they go in opposite directions, and so you get this reinforcement, this net reinforcement. Now, one difficulty in this experiment is you can't, or at least we haven't figured out a way to get rid of the classical forces. So this isn't a true topological phase. Although you get this Hamer-Keller-Wilkins phase, you also get what's called the dynamical phases, which are proportional to how long you are in the interferometer, and these are the origin of classical forces. This is where the atoms enter these beams and leave them. There you do get gradient, you do get a residual of the gradient force. And we haven't, and they're there, but the idea is that you have to set up this interferometer so that because they're the same on both arms, these cancel. So that puts some rather stringent requirements on the experiment. Another way to do the same thing is to have a vortex beam of light. And then, as I said, then you have your pointing vector has some component in the plane, and you pick up this rotation, just like in the Aronoff bone. You pick up this rotation as you go two paths around the center. And for the experts in the room who are worrying, isn't this the same as some of the experiments at NIST by Bill Phillips' group? There they had interference between a Laguerre-Gauss beam and a Gaussian beam. So they really have an intensity, a corkscrew intensity, and the atoms surf around this intensity gradient, whereas here this is pure phase, right? The only intensity here is like a Gaussian beam. Okay. And is this measurable? Well, you can do a back of the envelope calculation, which I guess I'm not going to go through in view of the time. But what you can check is that there's always a problem because there's a nasty factor of C in here, which is large. But it turns out that by working with atoms, which have this resonance response to light, you can achieve phase shifts which are of the order of milliradians. So it's perhaps possible, although there's also depends how far you can tolerate. You want to go as far away from resonance as possible. This is the line width, and this is the detuning, such that you don't have too much spontaneous emission, which will mess up your interferometer. Okay, so that's it. So what have I told you? I've told you that what I've tried to convince you is that Abraham and Minkowski were both right. And what Abraham was saying is, I don't think he was saying it at the time, but what we now appreciate is that Abraham is associated with the kinetic momentum, whereas Minkowski is associated with the canonical momentum. So depending what you're measuring, if you're measuring a diffraction-style experiment, you tend to measure the canonical. Indeed, quantum things, the momentum that comes into quantum mechanics is, in fact, the de Broglie momentum and things like this are the canonical momenta. So waves tend to have canonical momenta. Whereas particles, when you have some center of mass motion, like in the atom being the whole atom where it wasn't diffracting, it was being pushed by this plane wave of light, then it's more in the Abraham, and then it's the kinetic momentum. And this difference between the two depends really on the pointing vector. So you've got to worry, if the pointing vector is 0, there will be no difference. Okay, so the Abraham-Minkowski, I don't want to leave you the impression that it's quantum. It's a classical effect, but it seems to be connected in a deep way because its origin is, you can think of its origin is this D cross B. It's to do with velocities. You remember that the Lorentz Force is a non-integrable force. It depends on the entire history and so on. And this is the stuff of geometric phases. And so it's no surprise that that there's a quantum version where you get a geometric phase. Now you have Lorentz forces, you get geometric phases. And so what I'm proposing then is this is the optical version of the Hay-Michello-Wilkins phase. Who'd heard of the Hay-Michello-Wilkins phase before they came in this room? Just one of you. Okay. So maybe you learned something. And I propose that an atomic interferometer could do it, but more generally, you could perhaps have some very interesting, with more exotic beams, you can get much more, you can treat your, it's another way of getting, even for neutral atoms, neutral dipoles, getting them to behave like charged particles and feeling effective fields. Okay, so thank you for your attention.